Hello everyone. In this video, we shall discuss what are one-to-one functions, and we shall define inverse functions, and we will determine what is the connection of inverse functions with one-to-one functions. So before we define what's a one-to-one function, let's consider first the following relation R. So this relation is a set of ordered pairs containing 1 comma 2, 2 comma 3, and 3 comma 4. Now the question is this relation a function? So recall from our previous discussions that a set of ordered pairs is a function if there is no two ordered pairs with the same x coordinate. Or equivalently, if all the x coordinates are distinct. So in this case, since all of the x coordinates are different, then we say that this relation is a function. Now, if we try to interchange the x and the y coordinates of each ordered pair in the relation R, then we will get the relation S containing the ordered pairs 2 comma 1, 3 comma 2, and 4 comma 3. Now the question is this a function? So since all the x coordinates in relation S are distinct, then we say that this relation S is a function. Now this time, let's consider the relation U having the coordinates 1 comma 2, 2 comma 3, and 3 comma 3. Now is this a function? So if we check the x coordinates, all the x coordinates of the ordered pairs are distinct, so this relation is a function. Now, if we again interchange the x and the y coordinates of the ordered pairs in this function, we get the relation V with coordinates 2 comma 1, 3 comma 2, and 3 comma 3. Now, is this relation a function? If we notice, the second ordered pair and the third ordered pair has the same x coordinate. So which means that V is just a relation. It's not a function. So what's the difference between the relations R and U in the first two slides? Why is it that when we interchange the x and y coordinates of the ordered pairs in the two relations, the resulting relation in the first slide is still a function, and the relation in the second slide is not a function? It is because the relation R from the first slide is a one-to-one function. So it's a function because all the x coordinates are different, and a one-to-one function, its concept is defined in the following statement. Now, for every x, there corresponds exactly one value of y, and vice versa. So, which means that for every y, there should be exactly one value of x. Equivalently, we say that a function is one-to-one if all the x values are distinct or different, and also all the y values are also different. So that's why here the relation R is a one-to-one function. While the relation U is not a one-to-one function. It's only a function because the x coordinates are all different, but not all the y coordinates are different. So it's not a one-to-one function. So it's just a function. So to define formally what is a one-to-one function, a function y equals f of x is one-to-one if for each element of x, there exists exactly one value of y and vice versa. So algebraically or mathematically, one-to-one functions has the following property. If f of x sub 1 is equal to f of x sub 2, then we need to show that x sub 1 and x sub 2 are just the same numbers or values. So in order to prove whether a given function is one-to-one, then we can use the following definition. So for example, let's determine algebraically if the function f of x equals 2x minus 5, is a one-to-one function or not. So of course, though, we have to begin with f of x sub 1 equals f of x sub 2. And then later on, we have to show that x sub 1 is equal to x sub 2. So to evaluate f of x sub 1, we will substitute x sub 1 to 2x minus 5. So this will be 2x sub 1 minus 5. And f of x sub 2 will be 2 times x sub 2 minus 5. Now, if we add 5 to both sides of the equation, or if we transpose one of the negative 5 to the other side, then those two will just cancel out. So that's why we get 2x sub 1 is equal to 2x sub 2. And then if we divide both sides by 2, then we get x sub 1 equals x sub 2. So this satisfies the definition of a one-to-one function. So therefore, the function f of x equals 2x minus 5 is a one-to-one function. Okay, let's have another one. Let's determine algebraically if the function f of x equals x squared minus 1 is a one-to-one function or not. So again, we start with f of x sub 1 equals f of x sub 2. And then f of x sub 1 is equal to x sub 1 squared minus 1. And f of x sub 2 is equal to x sub 2 squared minus 1. So we get the following equation. If we transpose the negative 1 to the other side, then that negative 1 will just cancel out. So we get x sub 1 squared equals x sub 2 squared. Now, if we solve for x sub 1, we will be applying the square root property. So this would imply that x sub 1 is equal to the positive negative square root of x sub 2 squared, which is equal to positive negative x sub 2. So as you can see here, if we have x sub 1 corresponds to two values of x sub 2, one positive and one negative. Our requirement for one-to-one function is that x sub 1 should be equal to x sub 2. So in this case, if there are two values for x sub 2, the function f of x equals x squared minus 1 is not a one-to-one function. So this is the procedure to determine whether a given equation or function is a one-to-one function. How about whenever we have a graph of a function? How do we know if it is a one-to-one function? So it is through the horizontal line test. So graphically, a function is one-to-one if it satisfies both the vertical and horizontal line tests. So it should pass the vertical line test because it is a function, and it should pass the horizontal line test to determine if it is one-to-one. So the horizontal line test, similar to the vertical line test, states that if a horizontal line is drawn at any point of the graph of a function, and the horizontal line intersects in a maximum of 1 point, then the function is a one-to-one function. Now, in the case that the horizontal line will intersect in two or more points, then the given function is not a one-to-one function. Okay, so for example, let's consider this function here, which is y equals 2x minus 5. So its graph is a straight line because this function is a linear function. Now, if we draw a horizontal line at any part of the graph, the horizontal line will always intersect at exactly 1 point. So this function, y equals 2x minus 5, is a one-to-one function. It satisfies both the vertical line test and the horizontal line test. So this is one-to-one. Now let's have another example. So for example, we have the function y equals x squared minus 1. So this satisfies the vertical line test because this is a quadratic function. However, if we draw a horizontal line at this part of the graph, the horizontal line will cross at 2 points, which is more than 1 point. So which means that the function x squared minus 1 is not a one-to-one function. So, so now you know one-to-one functions, and one-to-one functions um, are a requirement for inverse functions. So what is an inverse function? If f of x is a one-to-one function, then there exists a function which we denote by f to the negative 1 of x, which is read as f inverse of x. It's called the inverse function of f of x, such that f of a equals b implies that a is equal to f inverse of b. So meaning the relation of f and f inverse lies on the interchanging of the x values and the y values. So for example, if we consider f of x is equal to 2x minus 5, the function value of 6. So if we substitute 6 to x here, that's going to be 2 times 6 minus 5, which is 7. Now, if we will apply the inverse function to 7, the value of inverse function of 7 must be equal to 6. Okay, so we note that if we solve for the inverse of f of x, the inverse is f inverse of x equals 1 half x plus 5 over 2. So if we substitute 7 here, 1 half times 7 is 7 over 2. And then we add it to 5 over 2, which is 12 over 2, which is equal to 6. So that's why f inverse of 7 is equal to 6. Okay, so how do we get this expression? How do we get this f inverse of x? So to find the inverse function, then the following are the steps that we should follow. So these are the steps in finding the inverse f inverse of x of a one-to-one function f(x). So first, we replace fx by y, and then we interchange the x and the y. And then we solve for y in the resulting equation from step number 2. And then number 4 will be replace y with f inverse of x. So let's have an example. Let's find the inverse of f of x equals 2x minus 5. So first, we replace f of x by y. So we're going to write it as y equals 2x minus 5. And then we interchange x and y. So therefore, we will replace this by x, we will replace this by y. So which means that we get x equals 2y minus 5. And then we solve for y in the resulting equation. So we have to transpose the negative 5. So we get x plus 5 equals 2y. And then we divide both sides by 2. So dividing this by 2 will give us 1 half x plus 5 over 2, which is equal to y. And then we replace y by f inverse of x. So that's why this is the inverse of the function 2x minus 5. So this example, this example is the one that we encountered in the previous slides. Okay, so what's the relationship of f and its inverse, f inverse of x? So both f of x and f inverse of x are one-to-one functions. So that means the inverse of f of x is f inverse of x, while the inverse of f inverse of x is f of x. So meaning they are inverses of each other. And then second, the domain of the inverse is the range of the function f of x. And the range of the inverse is the domain of the function f of x. So this is explained by the fact that in finding the inverse function, we interchange x and y. So which means the x from the function f will become the y in the inverse, and the y in the function f will become the x in the inverse. And then if we get the composition of f and f inverse, that's going to be equal to x. And if we get the composition of F inverse and F, that is also going to be equal to X. We will illustrate this later using an example. And then the graphs of the function F and its inverse are symmetric with respect to the line y equals x. So that means the points of f of x will be reflected along the line y equals x in order to get the points of the inverse function. Okay, so for example, the gray line here is the function 2x minus 5. The green line here is the inverse function of f, which is 1 half x plus 5 over 2. Now the blue line here is the line y equals x. So as you can see, the graph, the gray graph and the green graph are just reflections of each other along the line y equals x. And then if we get the domain and range of f, so the domain of the function f is the range of f inverse, and the range of f is the domain of f inverse. Now, notice that the original function f is a linear function. The resulting inverse is also a linear function. So that's why the domain and range are both all real numbers. So this is not a good example for the property that the domain of f is the range of the f inverse and the range of f is the domain of f inverse. Okay, so let's have a better example for that property. So let's consider, oh, by the way, before we go to the next example, let's verify first the composition of f and f inverse of x and the composition of f inverse and f of x. So according from the properties earlier that this is equal to, or both of them are equal to x. Okay, so first, let's try f of f inverse of x. So we know that f inverse of x is 1 half x plus 5 over 2. So we shall replace this by that. And then distributing the 2 here would mean canceling 2. So that means we will get x plus 5. And then there's a minus 5 here. So x plus 5 minus 5 is x. So this state is satisfied. And then the second one is f inverse of f of x. So this time we will use 2x minus 5 inside this parenthesis. And we will replace this by 2x minus 5. So that's why we have 1 half of 2x, 1 half times 2x minus 5 plus 5 over 2. So if we distribute the 1 half, we will get 1 half times 2x, which is x. 1 half times negative 5 is negative 5 over 2. And then we have the plus 5 over 2. So x minus 5 over 2 plus 5 over 2 will be equal to x. So this second composition is satisfied. So now going to another example. So to verify the property of the domain and range, let's use the following function. So find the inverse of f of x equals x minus 2 over 3x plus 1. So take note that this is a rational function, which you learned from the previous videos. So first, we will replace f of x by y. And then after that, we're going to interchange x and y. So we will be getting x is equal to y minus 2 over, x equals y minus 2 over 3y plus 1. And then here, we solve for y by multiplying both sides by the LCD, which is 3y plus 1. And then we get the following. So x times 3y plus 1 for the left side. And then the 3y plus 1 will cancel out. That's why we have y minus 2. And then x will be distributed to 3y plus 1. So we get 3xy plus x is equal to y minus 2. And then since we're solving for the variable y, we need to group all those terms with y on one side of the equation and all those terms without y at the other side of the equation. So yung y, we will transpose it from right to left, and then the x will be transposed from left to right. So we get the following. And then in the left side, we can factor out y. And here also we can factor out the negative 1. So that's why we have y times 3x minus 1 is equal to the negative of x plus 2. And then dividing this by 3x minus 1, we will get the inverse function, which is negative of x plus 2 over 3x minus 1. So this is the inverse of x minus 2 over 3x plus 1. We note that it just so happened that we just change the signs of this, but it doesn't always the case. Now, so let's check the domain. And what's the domain of this function? So since this is a rational function, the domain will be the set of all real numbers except the x values that will make this 0. So if we're going to equate this to 0, 3x plus 1 equated to 0, that would imply that x is equal to negative 1/3. So which means the domain of f is the set of all real numbers except x equals negative 1/3. And then since in rational functions, the range of f will depend on the degree of the numerator and the degree of the denominator. So since the degree here is 1, the degree in the denominator is also 1, and the degrees are equal, so the range will be the set of all real numbers except for y value that is equal to the quotient of the leading coefficients of the polynomial functions here in the rational function. So 1/3, so that's the exception, no? All real numbers except y is equal to 1/3. Now for the inverse, if we get the domain of this, we shall equate the x minus 1 to 0, and this implies that x is equal to positive 1/3. So that means the domain of the inverse is the set of all real numbers except x equals 1/3. Now notice that this is the value in the range of the original function. And then for the range, we will get the quotient of the leading coefficient, which is negative 1 over 3. So the range of f inverse is the set of all real numbers except y is equal to negative 1/3, which is also the value in the domain. So in here, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So this is a better example to show that the domain and range property of f and f inverse. Now the graph of those two functions. So our function f here is represented by the red graph, and our inverse is the purple graph, and then the green graph is the line y equals x. So if we're going to reflect this graph here to this graph here, we see that those two graphs are reflections of each other along y equals x. And then this graph here is reflected along y equals x, and it will result to this part of the graph. Now, due to the complexity of the computation, we will not verify the composition property of f and f inverse. Okay, and then finally, let's find the inverse of f of x equals x squared plus 1, where x is greater than or equal to 0. So why is it that we have a particular restriction on the value of x? So it is because the given function here is a quadratic function. And we know from the previous discussion that the graph of a quadratic function is a parabola that opens upward or downward. And in this case, since the coefficient of x squared is positive 1, the graph is a parabola that opens upward. However, since we're talking about inverse functions, in order for the inverse function to exist, the given function f must be a one-to-one function. But since its graph is a parabola, it doesn't satisfy the horizontal line test. So it's not a one-to-one function. Okay? So that's why we need to cut. No, we need to cut the parabola along its vertex in order to make this quadratic function a one-to-one function. So that's why we only consider x values that are greater than or equal to 0. Okay, let's try. No? If x is 0, the value of f of 0 will be 0 squared plus 1. So that's going to be 1. So which means 0 comma 1 is the point on this function. Now, if we use f of 1, still 1 is greater than or equal to 0. That's going to be 1 squared plus 1, which is 1 plus 1 is 2. So we have the point 1 comma 2. Now, if we use f of 2, so x equals 2 is still in this interval. So 2 squared plus 1 is equal to 5. So we have this point here. So this is the graph of f of x equals x squared plus 1, where x is greater than or equal to 0. So it's actually just half of a parabola that opens upward. So if it is just half, it satisfies the horizontal line test now. It will satisfy the horizontal line test. And thus we can determine the inverse. No? The inverse of f will also be a function. Okay? So in here for this function, the domain of f is x is greater than or equal to 0. And if we inspect the graph here, its range will be the set of all y values that are greater than or equal to 1. So its range is y is greater than or equal to 1. In interval notation, we write this as 0, comma, positive infinity. The range here is written as 1, comma, positive infinity. Okay, now let's take the inverse, no? So the inverse is, we need to replace f by y. So y is equal to x squared plus 1. And then we replace x and y. So x is equal to, we interchange x and y. So the equation becomes x equals y squared plus 1. And then we're going to solve for y. So transposing 1 to the left side will give us x minus 1 equals y squared. However, if we solve for y, we have to use the square root property. So which means that y is equal to the positive negative square root of x minus 1. However, we have to take only one sign for this. So the sign that we're going to adapt will depend on the domain of the original function. So since we're using here greater than or equal to 0, then we shall use the positive value of the square root. So we have to take the positive square root of x minus 1. So if we get the domain of this, so this is a square root function, the domain will be the set of all x such that x minus 1 is greater than or equal to 0. And if we solve for this is a linear inequality. We can transpose negative 1 to the other side. So that means it's the set of all x such that x is greater than or equal to 1. So that's the domain, which is the same as the range of the original function. So that's 1 comma positive infinity. And then its range, since this is positive square root, then the range will be the set of all y such that y is greater than or equal to 0. And in interval notation, we write this as 0 comma positive infinity. Okay, so if we try to graph this f inverse of x on this Cartesian plane, if these are the points of our function earlier, 0 comma 1, 1 comma 2, 2 comma 5. If we interchange these ordered pairs, we will be getting 1 comma 0. 1 comma 0 is here. And then 2 comma 1. And then we have 5 comma 2. So this is the graph of our f inverse of x. So if you notice, these two graphs, no, the graph of f and the graph of f inverse, are symmetric with respect to the line y equals x. And these are the graphs, no, from the GeoGebra online. Okay, so this ends our video for one-to-one functions and inverse functions. So I hope that you learned something from this video. And please do not forget to subscribe to my channel. Thank you for listening.